slide previously. Okay, so we are going today for the basic theories of measurement itself. This slide is credited to my colleague, Dr. Shafika, in University Technology Malaysia. So we are going to learn some types and categories of data classes of measurement, and then measurement standard. So when we speak about measurement, then actually what we are doing is comparing our measurement. Measurement is the things that we are measuring. The things that we are measuring. It's called measurement. The process of measurement basically is comparing that measurement with a certain standard. And the certain standard is something, either a thing, either an object, or otherwise could be a procedure that is known for certain to have the value of that parameter with the value. So we are comparing the measurement relative to the standard, and this process is called as measurement. So while comparing that, usually we do in multiple times. Very seldom in any experiments or observation, you only measure your parameter one time. Then if you measure only one time, then it cannot be trusted. At least you have to measure 3 times. That is the basic number of measurement that you need to do in order that you have reliable measurement. Even that 3 number is minimum. We call it triplicate measurement. Is the minimum number. Actually, it needs more. Later we learn why 3. Actually, you have learned it in the statistics class. Then we will learn about variations and errors. That is caused due to the measurement in multiple times. Then relationship, estimation, and hypothesis related to measurement, factors in making measurement, and errors when we do measurements, measurement errors. Okay. So biomedical measurements is related with the measurement of many information, informations inside our body, and this information could be in various energy domain, as we have discussed in previous chapter. That basically information is basically an energy. However, we are not concerned with the quantity of energy in measurement or sensing. We are concerned with the quality of the energy, what we call as information. So within this human body, there are many domains of information. It could be either biological, chemical, electrical, thermal, hydraulical, pneumatical, physical, magnetic, mechanical, dynamical. Many other types of system can be found. Each of these systems communicate internally with each other, with other systems within the body, and can also communicate with an external environment. So with the help of a multi-level control system and communication network within the body, these individual systems are organized to perform many complex functions. So like we have learned in the previous chapter, that how the respiratory system works in collaboration or in conjunction with the circulatory system and also with the heart pumping system in order to perform the exchange of gases from the body and with the surrounding atmosphere. And then the circulatory system works to exchange that gas with the cells and tissues all around the body. To obtain a valid measurement from a living human being, it is necessary to have deep understanding of the subject on which the measurements are being made. This is why we had to learn what we have learned in the previous 4 weeks. We have to understand where do those biosignals come from, and the related physiological phenomena. Of course, 4 weeks is too short. 4 weeks is actually too short. That's why we only cover the major biological system within our body: the heart, the muscle, the cellular, the neuron system, the respiratory system, the circulatory system, and some vital signal related to the system. But at least we have got some idea of how these biosignals are generated within our body. Yeah, and what kind of physiological phenomena underlie each of these biosignals. So measurement in the biomedical field can be classified into two types. When it is done in the living system, directly inside the living system measurement, we call it in vivo. So in vivo measurement is made within the living organism itself. For example, when we put pressure sensor inside the chambers of the heart to measure the actual pressure. We also had learned in the previous chapter about invasive blood pressure measurement, where the catheter is being inserted into the blood vessel, and this catheter is connected to a pressure transducer. This is also called as in vivo measurement because it is done in the living system of the subject. So otherwise, when a device is inserted into the bloodstream to measure the pH of the blood directly or other biochemical parameter, this is also in vivo measurement. When, however, we only sample the tissue or the cells or whatever from the body, and then we do the measurement, we conduct the measurement outside the body, in the lab or outside, anyway, outside the body, even though if it is near the body, but it is still outside, then we call such measurement as in vitro measurement or in glass measurement. For example, when we measure blood glucose level, if you go to any pharmacist or drugstore, like then they now already sell this blood glucometer for public, and usually the blood glucose is measured by first pricking the patient or the subject finger with certain device, and then the blood sample will be dropped onto the surface of the biosensor of the sensor strip. The sensor strip then is already connected usually in an electronic reader to measure the level of glucose inside that blood drop. Okay, so the sample is taken from the human body, the subject's body, but then the measurement itself, where the level of blood glucose is compared with a certain standard of inside the electronic system, is done outside the living body. It's done separated from the subject's body. So this is called in vitro measurement. Another example, of course, measure of pH, sample of blood that has been drawn from the patient's body. And actually, many of the clinics, clinical lab that we can find, usually conduct their measurement in vitro. Yeah, when your doctor asks you to do certain blood tests, in order that he or she can perform the diagnostic, can be sure about the diagnostic, we will ask you to go to this or this lab, and then the lab will sample the biochemical fluid from your body, either blood, urine, or saliva, maybe sometimes sweat or tears or faces sometimes. And from there, they put it inside in the lab, inside a certain analyzer, inside a certain instrument that the instrument can calculate or can measure the parameters inside the blood. How many the white blood cell amount, red blood cell amount, thrombosis amount, what else? Glucose level amount, etc., etc. Yeah, and the measurements are done outside the human body. The sample is taken from the human body, but it is done, the measurement itself, the process of comparing the sample with the standard is done outside. This is called in vitro measurement. So this is the illustration. When you do in vitro, you put the sample, for example, in this case, in glass well plate, sometimes in beaker or etc., or in cuvette, human stem cell. In vivo assay, when the measurement is done in the living system itself. Yeah, in vivo like this, when you are directly measuring from the living subjects in vitro when you are uh, collecting the samples, and then take them into the lab. So based on how the measurement is done, we can have either direct or indirect. Indirect measurement, you hold the measurement up to some calibrated standard and comparing the two. So you compare directly the measurement and to the standard. For example, here, when you are measuring the length to cut a paper, for example, or to the length of anything, you are measuring the length of that paper into the scales that are printed in that stainless steel ruler. Okay, so by comparing them, you know what is how long is that particular paper. Similarly, like this, when you are measuring blood pressure, this is indirect. Yeah? On the other hand, yeah, opposite to directly measuring in like the ruler, when you are measuring not the actual measurement but some other parameters which is still related to the actual measurement. For example, here the non-invasive measurement of blood pressure. Okay? Direct measurement, of course, you need to have you use catheter. You have to use catheter inserted into the blood vessel, and this catheter is connected to a pressure transducer, which is then connected to a pressure standard. And this is, of course, cumbersome. It is usually only done for patients in ICU, which needs constant measurement of his or her blood pressure. If we are for the purpose of monitoring health, for example, then we use this kind of sphygmomanometer, yeah, or tensimeter, blood pressure tensimeter. So we have learned actually, yeah, in the previous chapter that what we measure is not the actual blood pressure, but we put cuff, yeah, relative to this cuff. The cuff will put pressure to the blood vessel, the brachia, yeah, in our arm. Yeah. Then when the cuff pressure is released, okay, the first flow will correspond to the systole blood pressure, yeah, of our body, and that is we measure it also by putting our stethoscope, yeah, to hear the first flow of the blood. Then after the flow of the blood, the sounds reside. It has this oscillation, and the last one before it finally there is no sound anymore, and that will be the diastole blood pressure. So this is the indirect blood pressure measurement. The blood pressure itself is compared with the pressure of the cuff. Okay, so not the actual blood pressure inside the vessel, but instead is how the blood vessel itself try to resist this pressure from the cuff. So this is called as indirect measurement. Null measurement is, on the other hand, when we adjust one of the parameters. We compare the calibrated source to the unknown measurement, and the difference between the two should be zero. So when there is a difference, we try to adjust like this using a potentiometer, for example, to adjust such that then the difference between the unknown measurement and the parameter is zero. So how much we turned that sensors to make the difference to become zero indicates the value of that unknown measurement. So in this case, in the potentiometer, when we turn it, and then we find how much we turn until the resistor, for example, becomes zero, yeah, then it is the value of that measurement. So this is called as null measurement. So null measurement, we adjust the parameter, yeah, inside that sensor or inside the instrument until it balances. This is one of the principles also used in measuring weight in some of the balance. If you see, maybe you never see it there. So this is in when I was also kids. There is a balance that is the using moment, using moment, the thing, the object whose weight we want to measure is put onto the pen like this, and then the what you call it, the beam will be tilted, and then we try to slide in a certain weight in order that it is balanced, the moment is balanced, and then the number where we adjust that mesh inside that ruler, it looks like a ruler, will indicate the weight of that object. Okay. So after we do measurement, after we compare either these three, the unknown measurement to a calibrated standard, either directly or indirectly, or using null measurement, then we will have the data. Then we will have number representing that comparison. If, for example, it's the same as the calibrated, we do it by the calibration method. Then with certain standard, we compare it with that standard. Then we will have the number. Either it is the same as the standard, how many it is larger than the standard, or lower than the standard, and etc. If the data is non-numerical, then we call it as qualitative data. So for example, it could be nominal. There is no inherent order or rank, such as name or labels. It could be ordinal, which allows ranking. The difference between data points are meaningless. So ordinal, like order, but there is no, the difference itself doesn't have any meaning. It's just order the first, the second, the third. Yeah, this is also qualitative data. Alternatively, we could also have quantitative data, where the measurement itself give number. For example, it could be given, it could give an interval, a meaningful comparisons of differences, but not the relative values of two or more factors. Ratio, this is based on some fixed or natural 0 point. Yeah, natural 0 point, then the value of the measure will be based on the ratio to this fixed 0 point or natural 0 point. In either way, so in quantitative data, you have number. In qualitative data, usually you have labels. You classify. For example, like, is the subject, is the student male or female? This is qualitative data, male or female. Yeah, is the student the first in her class, in the class, the second in the class, in terms of order, in terms of rank. This is also qualitative data. But for example, if we ask how many male numbers are there in the biomedical engineering semester 4, this is quantitative data, because we have to represent that as a number, only one, for example. How many female students are there in biomedical engineering 4th semester? This is also quantitative data, 3, for example. So, as we have mentioned, we discussed earlier, that the process of measurement is basically comparing the unknown parameter with a certain standard. So at the field itself, at the lab or at the laboratory or the workshop, then usually the workshop or the lab should have a working standard. We call it working standard or shop level standard. So before usually you conduct a measurement, you need to always calibrate your instrument or gauge, your sensor. So this can be any form. For example, if it were a balance, then you have usually a standard of 5 gram, 10 gram, 50 gram, 100 gram, 500 gram, 1 kilogram, etc. So you put this this weight onto the balance and then measure it correctly, and another one at the balance, and it should measure correctly, etc. So you have then, you can draw the calibration chart. Okay, so this is what we call as the working standard. that small weights. Usually we have it in one single box, different types of it. Depending on the measurement we want to do, we need to do that calibration. For example, sometimes the balance will behave differently when you measure small weight compared to when you measure larger weight. Okay, calibration is something you need to do. And then that working standard itself has to be calibrated as well. Yeah, how do we know that standard weight, for example, 100 gram is really 100 gram? So its weight should also be measured in a laboratory, in a standardization laboratory, and at which then it is compared with a working standard. So this comparison between the lab standard or workshop standard with the working standard is done in a nationally certified laboratory or at the IST here. And IST here is in the US, National Institute of Science and Technology. If it were in, okay, where is annotate? I not do annotation. Oh yeah, here. Okay, so in Indonesia itself, for example, if for biomedical instrumentation, we usually do this at BPFK, okay, BPFK, Balai Penyelenggara, if I'm not mistaken, Fasilitas Kesehatan. This is under the Ministry of Health, yeah, MOH, Kementerian Kesehatan in Bahasa. And we have only maybe not that many numbers of BPFK, maybe 4 all around Indonesia. Alternatively, we have also private laboratory, private labs who has this working standard, with this working standard that can be used to calibrate your the shop level standard. Then, how do we know that the working standard owned by these labs, BPFK private lab, can indicate the correct amount, the correct quantity of that information? Yeah. Now, for that purpose, this working standard in this BPFK or private lab has to be calibrated in the second level national standard, using transfer standard. Usually, then it is only at one laboratory in the whole Indonesia. In this case, this will be at BSN, Badan Standarisasi Nasional. Previously, it was with LIPI, Pusat Teknologi Metrologi, but now it's all done by BSN. Then after that, the BSN has this second level national standard, which is of second quality. But then the second quality has to be also calibrated maybe once every year or once every, I don't know, with a national primary standard, which is maintained at the national level as well. At the national level, but they are not used frequently as the second level national standard. This serum is in Malaysia, and I think in Indonesia it is also BSN, which is the national primary standard. Okay, and finally, when later the national primary standard also, how do we know that its value is correct universally? How do we know that? Because all the bottom level standard is measured according to this national primary standard. So if this national primary standard is not guaranteed to be correct, to be accurate, then all the lower level standards, until the lowest level measurement, will also be false, will also give false result or inaccurate results. So in order to maintain that accuracy at the national level, at the international level, then this national standard is also calibrated against or with the international reference standard agreed by the International Standard Institute. And now it is getting more as of procedure. Previously, for example, the standard for 1 kilogram is a platinum with a certain volume that has a mass of 1 kilogram stored in Paris in the international standard institute. But now they changed this this standard into, I think, an atomic level, atomic standard, something which is not which doesn't change with time easily, because if it is in the form of object like that, it can corrode, yeah, maybe with humidity, etc. Yeah. Usually, of course, it is stored under a very strict environmental condition, but still it can change with time. Okay, and now I think they have a better standard. Although I forget, yeah, now it just changed recently in several years ago. The standard of length is still fixed. Yeah, it hasn't changed yet. So I think how many times the frequency or the duration, yeah, of certain atom. Yeah, you can check later. And so for each of these measurement, it has this international standard. What is the standard for time, the standard of mass, the standard of length, etc., etc. Okay, and that international reference standard will be used to calibrate the national primary standard. So actually, yeah, when we do measurement, yeah, what we are done at the lab level or workshop level has to be calibrated according to this lab level standard, yeah, shop level standard. And that shop level standard has to be calibrated against the working standard at nationally certified laboratory, or yeah, either government owned or private owned. That working standard at the national certified laboratory has to be calibrated against the second level national standard, and then to the national primary standard, and eventually to the international standard. This principle is what we call as traceability. Okay, traceability. It means what we measure at the shop level standard should conform eventually to the international level standard. Yeah, its accuracy can be traced to the international level standard. Okay, it doesn't stand alone. It's not stand alone. So if your instrument or a sensor is never calibrated, yeah, then it means it cannot be traced. It just cut the link. There is a missing link in the measurement. Okay, that is why yeah, if it is for your own use, maybe it's okay. But if it is, for example, you are opening a surface, yeah, in calibration, in instrument calibration, for example, calibrating ECG, electrocardiography, yeah, then you are basically opening a nationally certified laboratory. Your laboratory for standardizing the ECG has to be also certified, and the certification includes a comparison, a calibration with the second national standard, which is then traceable to the national primary standard and international reference standard. Okay, understood? Yeah. So this is the what we call as traceability. Okay, so since we have to do measurement multiple times, never should we only do the measurement if you are later doing experiments or for your projects or anything. You cannot measure only just one time. Okay, you need to measure multiple times. Okay, so with the multiple time measurement, then you will have an average, what we call as average or arithmetic means. This is the sum of all values divided by the number of the measurement. If you do 4 measurement, this is divided by 4x1, x plus x2 plus x3 plus x4. If you do 10 measurement, this is you have 10 data, then you divide it by 10. So you have the average of the 10 measurement. Yeah, this is an example. You have how many? 6 data, 6, 4, 5, 4, 8, and 3. You add them up and then divide it by the number of data, which is 6. You obtain 5. This gives you the mean, yeah, or the average, the arithmetic mean. We can also have the median of that measurement. This is the middle value of the data. And to obtain the asymmetrical, to have asymmetrical data due to outliers. For example, you have a range of data 1, 2, 4, 7, 8, 9, 18, 17. The middle will be this is 3, this is 3. There are how many? There are 7, sorry, 8 data, right? 8 data. The half, the median, the middle value of data will be calculated as the middle between the fourth and the fifth. In this case, it will be 7.5. There's also what we call as mode. This is the most frequently occurring value in the particular data set. For example, we have the data value set from 0 until 14. In this case, the value 9 appears 3 times during the measurement. Yeah, and the others only appear 2 or less, or 1 time, or even 0. In this case, the mode of this data set is 9. Okay. Besides the arithmetic mean, where we add the data, or all the data, and then divide it by their number of the data, we could also have geometric mean. Yeah, this is used for asymmetric data, the data which is not evenly distributed or linearly distributed. And usually we need then to use logarithmic scale. For example, let's say one day, the first day we spend 48,000. Let's just change this to rupiah. 48,000. Second day, half amount of this 48,000 of the first day. The third day, half from the second day. The fourth day, half from the third day. So then we tabulate, it becomes 48,000, 24,000, 12,000, and then finally 6,000 at the fourth day. So if you draw this linearly, what you will have is this kind of graph. But you could also draw this as a multiplication of 2. Yeah, the x-axis you draw as a logarithmic. Yeah, so you can have then a linear, a straight line. Here, since it is not linearly changing, yeah, with time, in this case the time is day, we can express the geometric mean, yeah, using this logarithmic scale as like this. So the geometric mean is calculated to be equal to the anti-logarithmic of the log of each of this value, and then divided by the number of that data, which is 4. The logarithmic of A, the logarithmic of, in this case, will be 48,000. Logarithmic of B, 24, plus logarithmic of B, 24,000, plus logarithmic of C, 12,000. Sorry, 24,000 and 12,000 and 6,000 for D. Divided by 4, and we conduct the antilog of it, and then here we obtain 16.97 or 16,970. Yeah, so this is the geometric mean, and when the distribution of the data itself is not evenly distributed but asymmetrical, where we need to use logarithmic scale to display the data. There is also what harmonic mean. Yeah, this is when the data is expressed in ratio. Yeah, for example, miles per hour, dollars per thousand. For example, here, let's compare the price of X 1 month. Let's say here in ringgit again. If you change, let's consider this 2,290. Week 2 is 1,980, 1,560 rupiah, 2,040 rupiah, for example. Then the harmonic mean is expressed as the ratio, yeah? 1 over A here, 1 divided by 2,290. Let's say 1 plus 1 over B plus 1 over C here, plus 1 over D, and then divided by 4. And this is being inverted. So then here we obtain the harmonic mean to be 1.93. Okay. This is harmonic mean. If we have the data is continuous, not as sequence of numbers as before, how to get the average? And we can get the average using integral, yeah, where the average of the data will be the area under the function curve divided by the interval between them. Yeah. So in this case, we have this faults, yeah, V1 faults allow from T1 until T2. What is the average of the signal? Yeah, the average of the signal. Then what we can do integration of this the value of x here, or the signal from T1 until T2 divided by the time interval between T1 and T2 is T. Yeah, and since this is constant, then of course we will have P1 here. Okay, but if it is not constant, then we will have the average, the integrated average value. There's also root sum square, RSS. This is used when pieces of different data are combined to form a single number, even though they are not correlated to each other. For example, for noise in electronic circuit, the noise may come from different source, white noise, the junction, the Johnson noise, etc., like the short noise, etc. So in this case, the PRSS root sum square is calculated as sigma I from 1 until n Vni squared. Vni here represents the particular noise type in that electronic circuit. There is root sum square and there is root mean square, RMS. Yeah. Here, this is when after you square the value, you do the integration, divide it by the period, the interval of that integration, and then you put square roots. Yeah, here of that value. This is voltage root mean square. The VRMS, the RMS value, the T is the interval, the time interval. If you do integration from depending on from where you do the integration from, okay. And then the voltage T is the time varying voltage function. Here the VRMS usually is used to represent the energy. Okay, as you have learned in the electrical engineering 2, electrical circuit 2, energy or power, something like that. So if it were sinusoidal, here the value of the VRMS is 0.707 of the peak voltage of the VP. Yeah, half square root of 2. Okay. So when we do measurement and then we calculated the data, I mentioned to you that at least you have to do three times of the measurement. We call it triplicate measurement. Why is that? Because we need to know the spread of data about the mean. Yeah, the spread of data about the mean. So if you have the mean in the middle, the spread should be then indicated by the value, certain value below the mean and certain value above the mean. This cannot be calculated unless you have properly, unless you have triplicate measurement minimum. Of course, if you do more measurement, 4 times, 5 times, 6 times, 10 times, that will be better, much better. Okay, the value of the standard definition, which represents the spread, is calculated using this formula. Yeah, using this formula, S equals to square root of sigma inside the xi minus x squared minus x over bar and squared divided by n minus 1. Okay. So here the x represents the average, yeah, or the mean. This is the mean. And the xi here represents the value of that x, the parameter at ith measurement. Yeah, the value of x at ith measurement. Yeah, the first measurement, second measurement. So you calculate the difference between that value with the mean, and then to eliminate negative sign, yeah, negative or positive. So we don't really care about whether it is larger than the mean or smaller than the mean. As long as it has a difference with the mean, then it will have value, right? If it is the same as the mean, then it will be 0. So then you make spread and divide, then sigma add between all the data set, then divide it by the n minus 1, and then put a square root on that value. So here, this is only valid when n at least equals to 3. And when n is 2, only you cannot have spread here. 2 minus 1 is 1. Yes, you still have value, but that doesn't represent as spread because it is only divided by 2. Okay, it has to at least by 1, So 1, then you don't have spread. It's just then it will be just the difference between the xi minus the x mean, right? For example, you have only two data set, and the other one plus the difference of the second data, okay, to the mean. Then this is being added up. Then you divide it by 1. So you cannot have, this is not spread. Okay, you will only have spread with at least 3. You have the spread of data 1, data 2, and data 3. The difference of each of the data 1, data 2, and data 3 with the mean. You add up this difference after being squared, of course. Then divide it by 2. 3 minus 1 equals to 2 to have the data spread. So here, if we represent it, if this is the x mean, the sigma actually represents this spread, how well it is being spread here. In statistics, usually, we have what we call a 6 sigma. So the value here is 3 sigma, and this value here is also 3 sigma. So the value within the 6 sigma, from minus here, this is x minus the 3 sigma, and this is x plus 3 sigma. This value of the 6 sigma represents 95% of confidence that the measured data will lie over this curve, not beyond this curve. Okay, so that's why you have also later the p test, the p test, where you have this 95% confidence. Okay. Okay, sorry. I have to delete this first. Use with mean for symmetric distribution. Here we call it symmetric distribution. 75% is always between x minus 2s and x plus 2s. While if you want to have 95%, 95% is always between x minus 3s to n x plus 3s. Okay. Then we can also have what we call as variance. When this is squared, so means the square root gone, the square root is gone. So only sigma xi minus x over bar, or the mean square, divided by n minus 1, that become the variance. So, s square or sigma square. The coefficient of variance is obtained by standardization of the variation for comparison of distribution measured on different scale. So this is obtained by dividing the s, the sigma here, by the average, times 100%. And the sigma times 100%. Sigma divided by average, or by the mean, the x mean, multiplied to 100%. The standard error of the mean SEM expresses the variability to be expected among the means in future sample. And this is calculated also from standard deviation, S or sigma, divided by the square root of n minus 1. Okay, so this value divided by square root of n minus 1. Or, so if this one is this, divided by n minus 1, so basically then annotation. Okay. So this will be square root of sigma xi minus x over bar, the mean square. Then n minus 1 here. Okay. So what we will have is square root sigma xi minus x over bar square divided by n minus 1. So the n minus 1 is not under square root anymore. Okay. So there we have the standard error of the mean. It expresses the variability of the expected among the means in the future sample. Okay, let's have a break now for this basic theories and measurement, and we will